Okay, our last video on free fall, and what we're going to do right now is take a look at some patterns or trends that you should be aware of that can help you solve problems a lot easier than otherwise you would have. So the situation here, let's assume that the acceleration due to gravity is 10 meters per second squared, just for a nice easy number. Let's assume that you're starting from the origin, and you are starting, an object starts at the origin, is dropped from rest, and that down is positive. So we're assuming that something can fall for up to 8 seconds here, and I mean 8 is arbitrary. We're just trying to get the trend of how does the velocity and the distance fallen change after every second. You can see that we have columns here for time, velocity, and distance fallen. And our job is to just fill out this chart and see what patterns can emerge. So let's fill out the first part. We know that the initial velocity is 0 seconds because it's dropped from rest. We know that distance fallen is also 0. Now, let's see here. After 1 second, we want to be able to figure out the velocity. So let's think about what we know, and I'm going to write it off to the side here. We want to know the velocity. We know the initial velocity is 0 meters per second squared. We know the acceleration is 10 meters per second squared, and we're going to leave that as positive because we're saying that down is positive and the acceleration due to gravity does point down. And the time, well, the time is going to change throughout here, okay? So the time, I could plug in 1 second, I could plug in 2. Let's just say 1 second for right now. All right, now how could I figure out the final speed? Well, we have an equation for that. It's the equation that's the rearrangement of the definition of acceleration. V equals V naught plus AT. Now, if V naught is 0, then this lends very easily to A is 10 meters per second squared, T is 1 second, so V is 10 meters per second. So I plug in 10. Now, let's think about how that pattern repeats as we go on for more and more time. We can always take the initial spot as being the spot for what it was dropped from, and then just say that the time is however many seconds it's been since that initial drop. We don't have to plug in 10 for the initial velocity now. Let's just keep saying, hey, the initial velocity was 0. How fast is it going to be moving after 2 seconds? And what you'll realize is that this eventually leads us to this equation, where the final velocity is given by the acceleration multiplied by the time. And the acceleration is always going to be 10, right? So if the acceleration is always 10 meters per second squared, all we're doing is multiplying by the time, multiplying 10 by the time, and that's giving us our velocity. So after 2 seconds, that would be 20. After 3 seconds, 3 times 10 is 30, and so on and so forth. And as you should notice, it's a very obvious pattern. We see that the velocity is increasing by 10 meters per second every second. And if you stop to think about it, that's the exact definition of acceleration. Okay? Acceleration tells us how much the velocity changes every second. If in free fall the acceleration is 10 meters per second squared, another way of saying that is 10 meters per second per second. The change in velocity is 10 meters per second for every second that goes by. So if you want to know, okay, 4.5 seconds in, how fast is the object going? Okay, 4.5 seconds. At 4 seconds, it's changed by 40 meters per second. Another half second, that should be, well, half of 10 is 5, 45 meters per second. A lot of people don't realize that's what acceleration means. So, as far as velocity and time, we notice that the velocity is proportional to the time. If t doubles, so in instance, from 1 to 2 seconds, we have a doubling of the time, we have a doubling of the velocity. From 2 to 4 seconds, doubling of the time, doubling of the velocity, 20 to 40. It even holds if you look at if something quadruples. From 2 to 8 seconds, the time quadruples, 20 to 80, the velocity quadruples as well. That is what we mean by something being proportional to something else. So, V is proportional to t. If t doubles, V also doubles. And just one other note that I want to write down there is that the velocity increases by the same amount each time. Okay? And that will happen in the absence of air resistance, in the absence of the object hitting the ground. That will continue for forever, as long as the acceleration due to gravity stays the same. Now let's look at the distance fallen. That's not going to be quite as easy of a pattern to discern, but we can still find this fairly easily. We know that the initial speed, or the initial position, excuse me, is 0, and we're looking for that final position. So the equation I might want to use here, and I'm going to squeeze it in on this side of the paper. Hopefully you can see the whole thing. So I have x equals x naught plus v naught t plus 1/2 a t squared. Okay, yep, Good, you can see that whole thing. So we know that if x naught is 0, if it starts from the origin, and v naught t is also 0 because it starts from rest, this simplifies down to x equals 1/2. The acceleration, again, is 10 meters per second squared. The time is 1 second. We have to square that. So 1 second squared, still 1, times 10 is 10, times 1/2 is 5. Okay, well, so what we realize is, again, if we always take the initial values to be 0 for this, we always start from, where did it start from in terms of its position and velocity. All we have to do is change that t squared. 1/2 and a are going to stay the same. So we eventually get down to an equation that looks like this: 1/2 a t squared. And in this free fall case, we have 1/2 times 10 meters per second squared t squared. We end up with this: x equals 5 times t squared, which looks like kind of a weird equation. It's not really something we ever talked about last year, and it's not really that important that it's 5t squared, but that's going to help us to calculate these very quickly. If I plug in a 2 here, 2 squared is 4 times 5 is 20. Now, this doesn't seem like as easy of a pattern as before. We see that in the first second, the object falls 5 meters. In the second second, it falls 15 meters to a total of 20. I guess we could point out that 20, as the time doubles, the distance fallen quadruples, but there's not really it's not a super obvious pattern from before like the other one was. So let's keep going. If we plug in t equals 3, 3 squared for t equals 3, 3 squared is 9, times 5 is 45. And again, we see that, we have a quadrupling here. This is clearly not a quadrupling. It's a little bit more than doubling. But let's also go back and think about the pattern. From 1 to 3 seconds, our time triples. The distance fallen is looks like 9 times as big. So that's interesting. If the time doubles, we have the distance fallen quadrupling. If the time triples, the distance fallen should be getting bigger by a factor of 9. That's kind of interesting. I wonder if that holds. If we quadruple the time, then I wonder what the pattern will be. If time is 4 seconds, 4 squared is 16. 16 times 5 is 80. So when the time quadruples from 1 second to 4 seconds, the distance gets 16 times as big. So what is the relationship between something doubling and then something else quadrupling? Something tripling and something else increasing by a factor of 9. Something quadrupling, something increasing by a factor of 16. The size of the factor of change in the time, if you square that number, you get the size of the factor of change in the distance fallen. As a matter of fact, this keeps going. If we have 5 seconds, 5 squared is 25 times 5 is 125. Okay, 6 squared is 36 times 5 is 180. 7 squared is 49 times 5 is 245. And 8 squared is 64 times 5 is 320. And all the way down, that same pattern seems to be holding. Whatever the factor change in the time is, the distance fallen changes by the square of that factor. We can see that from 4 to 8. From 4 to 8, the time doubles. We should expect the distance fallen to quadruple. 80 to 320. 320 divided by 80 is 4. From 2 seconds to 8 seconds, that's a quadrupling of the distance fallen. So we should expect a factor of 16 difference in the distance fallen. And that's exactly what we get. Okay? So what we're saying here is, and you can see it in this equation right here, 5 is just a constant number. We see that x, or the distance fallen, I'm going to call it x, is proportional not to t this time, but to t squared. X increases as the square of the time increases. In other words, if t doubles, d quadruples, and so on and so forth. If it triples, it increases by a factor of 9. One of the interesting things is if you look at the differences between the distances fallen, you also see a similar pattern emerge. For the first second, it fell 5 meters, then it fell 15 meters, then 25, then 35, 45, 55, 65, and 75 meters. And this should be expected because every second it's gaining speed, it's traveling more and more distance. It's not traveling the same distance every time, it's traveling more and more distance. So we get this quadratic pattern instead of a linear pattern like we got with the speeds. So we actually talked about these two results earlier on we saw that if we talk about proportionalities on one of the first set of notes, this is mathematical justification. This is reinforcement of those patterns. Okay, so if you can remember that for free fall and any other constant acceleration situation in which you have these initial conditions, the velocity is proportional to the time, and the distance fallen or position, displacement is proportional to the square of the time. That can really help you to solve some questions very easily without getting way into the math, and it can allow you to check your predictions. Let's say you see a question, you say, okay, based on the basic relationships I know, I think this should be the answer, and then you do the math and you get something wildly different. That's a clue that either your initial assumptions were wrong, or you should go back and check your math. Okay? But in any case, this is just so that you can see that there are patterns to how this works. And the more you see this, the easier it is to solve similar problems. Okay? Projectile motion is next.